Hi everyone. In this video I'm going to talk about Lewis structures of molecules. Lewis structures are models of molecules that show us the type of bonds within and the distribution of valence electrons around different molecules. For example, carbon dioxide, CO2. We see it written like this, but is this kind of what it looks like in real life? Like, is it a carbon bonded to an oxygen bonded to an oxygen? Or is it a carbon in the middle of two oxygens? Are these single bonds? Are they double bonds? Are they triple bonds? Is it one single and one double? Are there lone electrons on the outside of these atoms? All of these questions get answered with Lewis structures. Lewis, named after the scientist who pretty much discovered the covalent bond and set up these types of models. So here are the steps. Now, without an example to work with, these make very little sense. So let's start with O2, oxygen gas. Let's talk about the structure of oxygen gas running through these steps here. So the first thing you're going to do, step one, is you're going to write the skeleton structure. Now, that's not a chemistry term. That's just a term that I use because it's like the backbone. A skeleton structure, which are just the elements connected by a single line. So in this case, we have O2. We have two oxygens, so I'm going to go O. Let me fix that a little bit. O, single line, O. The lone element will generally be in the center. Now, in this case, there is no lone element. It's two O's. But like, for example, let's say you have methane, which is CH4. With this, you're going to put the C in the middle, and you're going to branch it off all four directions like this, where you go H, 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 H. You're not going to put like an H in the middle and then have like H, 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 C. The lone element's always going to be in the middle like this. And in fact, when there are more than one lone element, carbon always takes the middle. It's known as the central atom. Carbon is often in the middle. Step two, put dots, pairs of dots around every element, except for hydrogen, to satisfy the octet rule. Now, when I say octet, what number comes to mind? 8. We've talked about this before. Every element behaves in ways to get to 8 valence electrons. So for example, a sodium has 1 valence electron. It wants to get to 8. What's the easiest way to do that? Get rid of its 1. Because we say then it gets down to 0, but in reality, once you shed that last valence electron, the next innermost ring, which is full, is the new valence shell. Or the opposite of that would be like a phosphorus. Phosphorus has 5 valence electrons. So what's phosphorus always trying to do? Gain 3 to get to 8. Now, why do I say except hydrogen? Well, hydrogen only has 1 electron, and it can only get to 2, although sometimes it can give up that electron, forming H+. You learned about that in the acids. So hydrogen can't get to 8. It can only get to 2. And a couple other elements as well, like a lithium, for example, has 3 valence electrons. Or sorry, lithium has 1 valence electron, 3 total. It would try to get to 0, which would get it to 2, not 8. Anyway, put pairs of dots around every element to satisfy the octet rule. So before I do that, note that each line, which is this line right here, or these lines here, each line represents a single covalent bond, which counts as 2 electrons for each of the atoms it connects. What that means is this oxygen has 2 electrons from this bond. And this oxygen also has 2 electrons. I know you're saying, well, how do they both have 2 if they're sharing? Well, that's just the way covalent bonds work. Both of these atoms are experiencing those 2 electrons. So this oxygen needs to satisfy the octet rule and get to 8. So what I'm going to do is add 2, 4, and 6, and that counts as our 8. This one here has 2, so I'm going to go 4, 6, 8 like that. Now, just a quick important point here. You're not putting the number of valence electrons that that element has around it. It's just coincidental that oxygen has 6 valence electrons, and I happen to put 6 dots. Just a coincidence. Every element's going to get to 8 electrons here. Just as another example, let's say we have nitrogen gas, which is N2. You would represent that as N bonded to N. And even though nitrogen has 5 valence electrons, I don't care. I'm not going to go like 1, 2, 3, 4, 5, or I'm not going to go this one counts as 2, 3, 4, 5. You're not going to do that. It's the octet rule. So all of these get to 8. So now this one has 2, 4, 6, 8. That's satisfied. This one here has 2, 4, 6, 8. It's satisfied. All right, going back here, my oxygen, my left oxygen has 8 electrons around it right now because it's 2, 4, 6, 8. This right oxygen has 8 electrons around it, 2, 4, 6, 8. Looking over here at my methane, look at carbon in the middle. We need to get carbon to satisfy the octet rule. But notice carbon already has 4 single lines around it. What's a single line? It's a covalent bond, which counts as 2 electrons. So this carbon's actually done already. It's done. It has 2, 4, 6, 8. These hydrogens do not follow the octet rule. Hydrogens can only hold a maximum of 2, and notice that each of these hydrogens already has 2. So this is actually done. You're not going to add any dots to this. Now, if this were something like a CBr4, where each of these are now bromines, well, bromine, of course, can follow the octet rule, so you would add dots around each of the bromines. Step 3, count the number of electrons in your skeleton structure. Now keep in mind, a dot is an electron, so this is a pair is 2. What else are electrons? The single lines. A single line represents 2 electrons. So I'm counting the total number of dots here. 2, 4, 6, 8, 10, 12, 14. Once again, these count as 1, 2. So I'm going to go 2, 4, 6. This counts as 2 electrons, so that's 8, 10, 12, 14. And I like to write that number down, 14. My methane here, 2, 4, 6, 8, like that. Number 4, looking at the formula and a periodic table, count the number of valence electrons in the molecule. So I'm going to look at my O2, or I'm going to look at my CH4, and I'm going to look at a periodic table and count the number of valence electrons. So you might need a refresher on this, but in the periodic table, the group name, when you use the A naming, that tells you the number of valence electrons. So this is group 1 or 1A. This is group 2 or 2A. Generally, we write this in Roman numerals, 2A. We skip these. This is 3A, 4A, 5A, 6A, 7A, and 8A. Or you can rewrite that, of course, in just regular numbers. The number before the A tells you how many valence electrons those elements have, with one exception. What's the one exception? Helium. Helium does not have 8 because it can only hold 2. So helium has 2, but like neon has 8, argon 8, and so on. So looking at my O2, how many valence electrons are in O2? Well, here's O. It's in group 6A, so each oxygen has 6. There are 2 oxygens. We have 12 valence electrons. My other example was methane, CH4. How many valence electrons in CH4? Well, here's C, 4. So carbon has 4. Here's H, 1. I have 4 H's. So that's 4 plus 1, 2, 3, 4. That's 8. 12 and 8. So my number of valence electrons from the formula is 12 and 8. Notice we have 2 numbers that we wrote down. One of them is by counting your dots and your lines. The other one is by looking at the formula. Step 5. If this number, meaning the one from the formula, matches your number of electrons in your skeleton structure, then you're done. Let's see, are we done? No. Are we done? Yes. What that means is, in this case, this model right here is the correct Lewis structure for methane. It's a carbon with 4 single bonded hydrogens. No lone pairs anywhere, lone pairs of electrons. Here, this is not the correct Lewis structure because the numbers don't match. All that, it doesn't mean we can't figure it out. It just means that the formula, the Lewis structure for oxygen gas is not 2 oxygens single bonded. So If your numbers don't match, make double or triple bonds until they do match. Here's how you do that. You look at any two adjacent atoms, meaning neighboring atoms that have lone pairs. The lone pairs being these dots. We call them lone pairs because even though it looks like they're all together, they're not. Like these two are by themselves, these two are by themselves, these two are by themselves. What you do is you remove a set of lone pairs from each neighboring atom. So since I have no choice, these are my only two atoms, I'm going to remove 2 electrons from here and 2 electrons from here. And I'm going to replace them with my double bond. Okay, very important that you don't forget to remove the electrons from both of them, not just one of them. And what you want to do is double check your octet rule. Are we still satisfying the octet rule? Well, my oxygen here has 2, 4, 6, 8. Because this is now 2 bonds. This is a double bond, which is 1, 2, 3, 4. So again, this left oxygen has 2, 4, 6, 8 electrons, meaning it's good. This one on the right, 2, 4, 6, 8, we're good. Now let's recount our number of electrons. 2, 4, 6, 8, 10, 12. See how we don't have 14 anymore, we have 12? And every time you take away 2 sets of lone pairs and make a double bond, you cut down by 2. And now we are done because my number of valence electrons from the formula matches the number of valence electrons in our structure. And what this means is that the Lewis structure of oxygen gas, which you're breathing in right now, is 2 oxygens double bonded together. And each oxygen has 2 lone pairs of electrons around it. All right, let's go through some examples. So for every example, I wrote the steps kind of simplified here, just as a refresher. All right, PF3, which we would call phosphorus trifluoride. First thing we do is we write the skeleton structure. Now, when you have 3 things, you put the central atom first. Now, why P in the center? Because it's the lone atom. Now, when you have 3, you generally go left, right, and up. And you put your F's here. Now, you might say, well, why wouldn't you like triangulate it like this? It's just generally not what you're going to do. And there's a reason for that. This phosphorus is going to end up getting a lone pair in the middle. So there are kind of 4 areas around it. So again, if you have a lone atom and then a triple atom, you go left, right, and up. Okay, step 1's done. Step 2, lone pairs of dots to satisfy the octet rule. So we have F's and P's. Do we have any hydrogen? No. That just means all of these get lone pairs. So this fluorine has 1 shared covalent bond. That's 2. Here's 4. Here's 6. Here's 8. This fluorine up here, same thing. This is 2 already. So we go 4, 6, 8. This fluorine, 2, 4, 6, 8. Don't forget your phosphorus in the middle. How many electrons does this phosphorus have right now? 2, 4, 6. We need to get to 8. Okay, just to make sure I'm very clear on this. This fluorine, you're not going to put 7 electrons around it because fluorine has 7 valence electrons. Same thing with this phosphorus. Phosphorus comes with 5 valence electrons. You're not going to get it to 5. You're going to get it to 8. Same with this. Okay, so that's step 2. Now this might be correct, it might not be correct. Here's how we can tell. First thing we need to do is count the number of electrons in this structure. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay, so I count 26 from my structure. Once again, each blue dot here is an electron, so I count them in pairs, 2, 4, 6. Now this line is 2 electrons, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Step 4, count the number of valence electrons in the molecule, meaning in the formula. So checking my periodic table, phosphorus is in group 5, or well, it's 15 or 5A, so that has 5. Fluorine is in group 17 or 7A, so fluorine is 7. There are 3 of them, which gives us 21. 5 plus 21 is 26. Look at my numbers, 26, 26. What does that mean? That means we are done. That means that the proper Lewis structure for phosphorus trifluoride is 1 phosphorus with a lone pair of electrons and 3 I almost said phosphide, 3 fluoride atoms single bonded to it. Okay. SO3, sulfur trioxide. All right, step 1, skeleton structure. So the sulfur is going to be in the middle with an oxygen on the right, an oxygen on the left, and an oxygen up top. Step 2, lone pairs of dots. So this oxygen has 2, so we go 4, 6, 8. This one up top, 2, 4, 6, 8. This one here, 2, 4, 6, 8. Don't forget your central atom, your sulfur. This has 2, 4, 6, and there's 8. All right, let's find out if this is correct. Number 3, count the number of electrons in your skeleton structure. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. 26. Step 4, count the number of valence electrons in the molecule, meaning from the formula. So checking the periodic table, let me just show this. Here's sulfur. How many valence electrons? 6. Here's oxygen. How many valence electrons? 6. So going back to my example, we have 6 here. We have 6 times 3 is 18 here. What's 6 plus 18? 24. Is this correct? No, because this number does not match this number. So how do we make it correct? Well, we need to turn a single bond into a double bond or even a triple bond until it works. All right, so how do we do that? We pick any 2 neighboring or adjacent atoms that both have lone pairs. So it's going to have to be this sulfur because none of the oxygens are bonded. Like this is not a legitimate bond. You can't make a double bond between that because they're not actually touching. So it doesn't matter which oxygen you pick. I'm just going to go with the one on the right. So let's make a double bond between these 2. I'm going to remove the 2 lone electrons from the sulfur and 2 lone electrons from the oxygen. Now, technically, you can pull that pair off the top or that pair off the side. It doesn't really matter, but I tend to do them at the same place. I'm going to replace that with a double bond. Make sure our octet rule is still satisfied. For this O, we have 2, 4, 6, 8. For this S, we have 2, 4, 6, 8, so we're still good. That should have knocked us down by 2. Let's double check. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Notice now the 2 numbers match, meaning this is the correct Lewis structure for sulfur trioxide. It's a sulfur atom with a single bonded oxygen, a single bonded oxygen, and a double bonded oxygen. And those single bonded oxygens each have 3 lone pairs or 6 electrons. And the double bond has 2 lone pairs. Okay, Br2, this would just be bromine. Bromine being a Brinkelhoff. So our skeleton structure is just Br, single bonded to Br. Dots for the octet rule. Okay, 2, 4, 6, 8. 2, 4, 6, 8. Number 3, count the number of electrons in your structure. So we have 2, 4, 6, 8, 10, 12, 14. Next, count the number of valence electrons in the molecule. Br2. Bromine is in group 7A, meaning it has 7. So Br2 is 7 times 2, which is 14. Change the single bonds to double bonds until the numbers match. They match already. We're good. That's bromine. Br2 is single bonded, just like that. HCN. All right, so we have lone element, lone element, lone element. Which one's going to be the center? It's going to be the carbon. Basically, when in doubt, carbon goes in the middle. Here's our carbon. And we're going to go left, right. It doesn't really matter which way you go. You can do the H here or the H there. I'll just stick to the way it's written there. So we have N and H. Okay, let's put dots. So here I have a hydrogen. Remember, no dots on the hydrogen. Hydrogen is an exception to the octet rule. It can only hold 2, and this hydrogen currently has 2. The carbon in the middle has 2, 4 electrons already, so all we need is a pair there and a pair there. This nitrogen has 2 already, so we go like that. All right, let's count them up. 2, 4, 6, 8, 10, 12, 14. As written, we have 14. Come on. HCN, hydrogen is 1, carbon is 4, nitrogen is 5. Again, if you don't know where I came up with those numbers, hydrogen is group 1A, so it has 1. Nitrogen is in group 5A, so it has 5. Carbon is 4A, so it has 4. 1 plus 4 plus 5 gives us 10. Is this the correct structure? No, because we have 14 and 10. All right, so the first thing we're going to do is make a double bond to fix this. So where does a double bond have to go? Notice hydrogen doesn't have any lone pairs, so it cannot have a double bond. So the double bond has to be between the C and the N. So I'm going to remove 2 electrons here, 2 electrons here. I'm going to make the double bond. And that should have knocked off 2. Let's double check. 2, 4, 6, 8, 10, 12. Are we good? No. So now we have no choice but to make a triple bond. So you do the same thing. You pull another 2 off the carbon, another 2 off the nitrogen, and you make this into a triple bond. Again, the octet rule is satisfied because this hydrogen still has 2, which is what it wants. This carbon now has 2, 4, 6, 8. This nitrogen has 2, 4, 6, 8. That should have brought us down by 2 to 10. Let's check. 2, 4, 6, 8, 10. 10 matches 10, and we're good. So that's the Lewis structure of HCN. It's a single bond between the H and the C, a triple bond between the C and the N. No lone pairs on the C, 1 lone pair on the N. Okay, just got a couple more of these. SiCl4. You might want to pause and try it and then play the video. So the central atom is the one that's by itself, which is the silicon. When you have 4, you go all 4 directions, up, down, left, right. We have a chlorine here, a chlorine there, and chlorine there. Dots. So each chlorine has 2. You need to add 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. The silicon in the middle has 8 right now, no dots on the silicon. All right, let's count them up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. All right, looking over here, silicon is right under carbon, which means it has 4. Chlorine has 7 times 4 is 28. 4 plus 28, 32. 32 matches 32. This is our structure. It's 4 single bonded chlorines. Each chlorine has 3 lone pairs, and the silicon in the middle has no lone pairs. N2, the most common molecule around you right now, 78% of the air is nitrogen. N bonded to N. Dots around each N. I think we did this one earlier. Okay, so the dots are done. Let's count them. 2, 4, 6, 8, 10, 12, 14. Okay. Nitrogen is 5, and 2 is therefore 10. Notice the numbers don't match. What are we going to do? Let's make a double bond. You cut pairs off the top of both ends. It doesn't matter which one you start with. I just happen to choose the top. And we go like that for a double bond. That should cut us down by 2. 2, 4, 6, 8, 10, 12. Yep. We're obviously not done. Let's pull another set of electrons off both of them. Make a triple bond. That goes down to 10. 2, 4, 6, 8, 10. 10 matches 10. And we're good. N2. You may wonder, why is it always the oxygen bonding with things like when we do labs? Why isn't it nitrogen bonding with things? Well, a big reason is that triple bond right there is harder to break than oxygen's double bond. If we go all the way back to oxygen, oxygen has, right, oh boy, way back, right there. Oxygen has a double bond, which makes it a little bit more reactive than nitrogen with the triple bond. All right, O3, this has a special name you've probably heard of, ozone. O3 is ozone. All right, let's draw a Lewis structure. So there are 3 oxygens, so we're just going to put them in a line. All right, let's add dots. So this one needs 6, This one needs 4. This one needs 6. Let's count the number of electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. O3, oxygen is 6, so O3 is 18. The numbers don't match, meaning we are not done. So all we need to do is make a double bond and we should be good. Doesn't matter where you make the double bond. Let's go between this one and this one. So I'll cut the top off these. I could have done the bottom. It's totally fine. I make a double bond, and that brings us to 18. Let's just double check. 2, 4, 6, 8, 10, 12, 14, 16, 18, and we're good. So that's ozone. It's a single bonded oxygen and a double bonded oxygen. And I think this is my last one. Yep. All right, CH3F. So the central atom could either be the carbon or the fluorine because they're alone, but it's going to be the carbon. Carbon is your central atom. Make that a little nicer. All right. So since there are 4 things bonded to that carbon, we got to go all 4 directions. There are 3 hydrogens and 1 fluorine. Okay, for our dots, hydrogen does not get any because it has 2 already and it's done. This carbon in the middle is done as well because it has 2, 4, 6, 8. This fluorine, though, needs lone pairs, and we now have our octet rule satisfied. Let's count them. 2, 4, 6, 8, 10, 12, 14. Once again, 2, 4, 6, 8, 10, 12, 14. Let's count this. Carbon is 4. Hydrogen is 1. There are 3 of them. Gives us 3. Fluorine is 7. 4 plus 3 plus 7 is 14, which means that's our Lewis structure. Okay, so you're welcome to do more examples. Let us know if you have any questions. Meet us in Zoom. Good luck.